If you have alkenes that have more than one group on it, or very different groups, such as tri and tetrasubstituted double bonds, we can't just use the cis-trans method. We use something called the EZ system, and we use the priority rules of Kane, Ingold, and Prelog, which is kind of what we did already. We just use the atomic number to figure out what has a higher priority and a lower priority. So an atom with a higher priority, like carbon, will have the atom number of 6, which makes it a high priority. Hydrogen has an atom number of 1, and so that has a lower priority. We break this carbon double bond in half. You find the higher and lower priority. If the higher are on opposite sides of each other, that makes it an E double bond. So this E stands for the German entgegen, which is opposite sides. If the higher priority groups are on the same side of the double bond, this is a Z double bond. Z is German for zusammen, same side. So the first rule is to rank the atoms that are connected at the comparison site. Higher atomic number gets higher priority. Bromine has the atomic number of 35. This goes down to hydrogen, which is 1, and that is the ranking there. And you can always go to the periodic table to see where these numbers are at. This is not some trend that you have to memorize. We start with cutting the double bond in half and looking at the first carbon, and we compare the atom numbers of H versus CH3. CH3 is bigger here. And then on this half, when we look at this carbon, we have Cl versus CH3. C has the atomic number of 6, and chlorine has the atomic number of 17, so chlorine is the larger group here. And then if we cover our double bond with the pencil, we can see one group is coming off of the top, the other is coming out of the bottom. So this is going to be E because it's opposite sides. So when we name this, this becomes E2-chloro, 2-butene. In this example over here, I'm going to look at the first carbon. You can cover up the second one if that's confusing for you. H versus CH3, this is CH3, and then you have CH3 versus Cl, and Cl is the priority one here. Cover up the double bond with the pencil. We have CH3 and Cl on the same half. This becomes Z, 2-chloro, 2-butene. If atomic numbers are the same, then you compare at the next connection point, which is at the same distance. For example, if I had a CH3 versus a CH2CH3, the carbons tie, so you go to the next atom out, then you're comparing H. You're going to compare H with C, so this one is higher. This is lower. In this example here, we have an OH versus OCH3. The O's are tied, so you go to the next atom out, which is H versus C, and C is higher here, so this is higher. So you just keep comparing until one of them has a higher atomic number. What you don't want to do is combine things, so you don't want to have an added effect. You want to compare the atoms individually. This carbon here is tied with this carbon. This carbon is bonded to another carbon, so is this one. So you'll look at the next atom. So we have a carbon with 2 C's versus a carbon and a hydrogen with a C. So this one has a higher priority than that one. This is higher. This is C to N versus C to Cl, C to CH3, C to H. So we don't want to add these because C to N is going to be larger than Cl to H. We're just looking at the individual atoms here. So C to Cl, this is higher. If you have a multiple bonded atom, that's equivalent to the same number of single bonds. So you can look at this aldehyde here. This carbon is double bond is kind of like being bonded to 2 oxygens. This oxygen is bonded to 2 C's. So when you're doing the ranking, it kind of looks like H, O, O, C. So this carbon is bonded to the 2 oxygens, and this oxygen is like being bonded to the 2 carbons. So you can use those rules to figure out the easy stereochemistry of each. I'll break this in half. I'm going to compare C to C. These are tied. So I have to go to the next one out. This is C to H versus C to C. So this is where the group wins there. Then I have a C to Cl. I'm going to look at the first atom where that's attached to this carbon. Cl is bigger than C. This is here. I cover up the double bond with a pencil. They're both coming off of the bottom half. This is Z. Here I have Cl versus O. After I cut this in half, Cl is bigger. Then I have C to C, which is C to C. This one has an extra one. This is the tiebreaker here. Those are on opposite sides of the double bond. This becomes E. In this one here, I have C versus H. And then I have a CN versus C to N. But this is a C triple bond N, which is like being bonded to 3 different ends. So this one is the winner there. This is E. So we're going to start looking at organic reactions. In my class, I like to divide them into 4 major categories of reactions. The first is a functional group transformation, where we change the functional group. We also abbreviate this as FGT. For an example, if you're changing an alkene to an alcohol, that's going to be a functional group change. There's also oxidations. So the oil rig analogy that you may have used in general chemistry, that applied to electrons. In this class, it'll apply to hydrogens. So oxidation is loss of hydrogen. Loss of hydrogen or addition of oxygen. So if you use oil rig in general chemistry, that applied to electrons. We can use that same analogy here in organic chemistry, but we're going to use it for hydrogen. Oxidation is loss of hydrogen. Reduction is gain of hydrogen. And then we have carbon-carbon bond forming reactions where we form a new carbon bond. For the most part, we're going to look at what's occurring in the reactions, try to figure out how it happens, and then see if we can use those common patterns to describe the changes. The first one that we're going to see is an FGT. There's a subgroup of those called addition reactions, and this is where 2 molecules will combine. So we have 2 reactants, ethylene here, which is an alkene with 2 carbons, with HBr, and so we get our carbon. So that was the same that was here before, the C with the 2 H's, and then we're going to add an H and a Br across the double bond. And the electrons that were in the double bond have donated themselves to make new bonds with the H and the Br. We can also see elimination reactions where a molecule is split into 2 different reactions. So this one reactant, ethanol, look at that group there. We add an acid catalyst, or the water is going to leave and take those electrons to form a double bond. We also get water as a side product. We'll also see a substitution reaction, and this results from 2 molecules exchanging groups. We have methane plus chlorine. Methane interacts with chlorine. We're going to substitute a hydrogen for a chlorine, and that will create chloromethane plus HCl. We may also see rearrangement reactions where a molecule can change the way it's connected together. In the case of 1-butene, an acid catalyst acts upon that. So the double bond has shifted its location. So 1-butene becomes 2-butene. So we get an isomeric product. Okay, so we want to try and classify how each of these reactions occur, or what is happening in each of the reactions. We start with CH3Br plus KOH, and we notice that there's an OH now on the CH3 and the KBr here. This is doing a swap out. So it's a substitution reaction. In this structure here, we have 2 carbons and a chlorine, and we end up with the alkene version of that. The chlorine is gone, and there's no OH here, so this is an elimination. Here we have CH2CH2. There is H2, which is added to the ethene. So this is an addition reaction. We've added the H's across the double bond. So the mechanism can describe how the electrons move, and so we can see the steps behind that and see what changes are occurring. Reactions will occur in defined steps that lead from reactant to product. There are steps that involve forming bonds or breaking covalent bonds, and these can occur one at a time, or they can occur in steps in combinations with other steps. If the bond making and breaking is happening at the same time, this is a concerted reaction. If it's happening one step at a time, a bond is being broken, in another step a bond is being formed, that's a stepwise reaction. When we look at reactions, especially in polar reactions, there's two things that are involved. The first one is an electrophile, which is something that loves electrons, and these usually tend to be electron poor species. A nucleophile is something that loves the nucleus. This is an electron-rich species. An electrophile will sometimes be abbreviated as capital E+. Electrophiles are usually Lewis acids. Nucleophiles are Lewis bases. So the electrophile is the acid. This is the electron acceptor. The nucleophile is a Lewis base, which is the electron donor. So what you're seeing here is a nucleophile, which is electron rich, has the extra electron lone pair. Electrophiles are electron poor, so it's positively charged. The nucleophile can give its electrons to the electrophile to accept, and then we get A, B. These electrons formed a new bond. Here are some examples of nucleophiles and electrophiles. So nucleophiles, if you recall, are electron rich. So the molecules where you see more of the red, these are all nucleophiles. These ones with blue areas or polarized areas, these are electrophiles. These are electron poor. In this one here, this is the H3O+, that is very blue, so this is positive because it's a positive charge. These ones here are polar. So we create an electrophile by making a partially positive atom being bonded to a partially negative atom. With this carbonyl, you have a partial nucleophile up here, but this carbon is acting as our electrophile.